Hello everyone, welcome to the course Data Structures. This is Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. And today's overview will be discussing about graph introduction. Under this, we will be discussing about graph terminology and graph representation. Okay, let us see what comes under the graph terminology. Here, first we need to know about what is graph. Graph is nothing but it is a collection of vertices connected to each other through a set of edges, right? And the study of graphs are nothing but it is a graph theory. And let us see how we are going to represent the graph in a formal definition. A graph is defined as an ordered pair of set of vertices. That means ordered pair means you are going to have something to be represented in the parenthesis, and it consists of set of vertices and set of edges, where we are going to represent like this. This is an ordered pair where it is going to represent the set of vertices and the edges. Okay, and let us see how we are going to represent a graph. Consider one example. This is a graph which is having the vertices, and let us see here these things A, B, C, D, E, which are representing with the circle. Those are nothing but the vertices, and the link between these AB and AC or the BD, anything, whatever the edges you are going to find, whatever the link that is you are finding between AB or BD or anything, these are nothing but the edges. Now, for a graph, if we want to represent what are the vertices and what are the edges, now you can see, you can write it in a set like this. Vertices are nothing but V, it is representing with the variable V, and here we are going to represent all the vertices. What are the different vertices we have? A, B, C, D and E. These are all the vertices. And what are all edges you have? This is one edge. You could look into here. This is one edge, A to B. This is one edge. In the same way, A to C you have, and B to D you have, and C to D and D to E. These are all the edges, right? And in this way, you can represent the vertices and edges. And let us see what are the applications where we are going to use these graphs. These graphs are mostly or extensively used in designing circuit connections, right? When you are going to see our electronic devices subject, in that you may be seeing different circuits or being connected like this way, right? And in that particular cases, we are going to use this graph theory, and we are going to use in other organizations also. Types or organizations or connections are named as topologies. In this, topologies means we have different types of topologies are there. What are the different topologies? You have star topology like this way. If you are going to represent, this is also a graph. And you have a bridge topology like this way. You have some bridge. And you have series topology. In these things, series, parallel, all these things you will be knowing and in the subject called design circuit and connections. There you will be knowing about what is the series and parallel connection. In that designing circuit connections, we are going to use this graph terminology. And not only that, the relationships among interconnected computers in the network follows the same principle of graph theory. Here, when you are going to make the connection between the computers networks, there also we are going to use this graph theory. And the parsing trees, these things you will be knowing about in the compiler design subjects where you are going to study in further. And there you will be knowing about, if you have given some grammar, right, for that grammar, how we are going to represent a parsing tree. For a grammar, suppose you have E plus E, this is a grammar that was given. And for this, how we are going to construct a parsing tree like this. This is a parsing tree, how we can represent. And routes between the cities are represented using graphs. You can see the Google Maps. There also we are going to use the concept called this graphs. These are the applications where you could see. And let us see some terminology where we are going to use in graphs. Here already we have seen about what is a vertex and what is an edge. individual data element of a graph is called a vertex, and vertex is also known as a node, where we are going to represent with a circle. And as we have seen in the previous example or in this example, the vertices are A, B, C, D, E. These are all the vertices. And let us see the edge. An edge is nothing but it is a connection between the two vertices, and this is also known as an arc. Edge is sometimes called it as arc also. And an edge is represented as starting vertex and ending vertex. It is going to be represented. Suppose I am going to have a connection like this, connection between two vertices, and the starting and ending we are going to represent in an edge. This is the one. And here you can have, in this diagram you could see the 7 edges are present. What are those? AB, this is one connection, and AC, then you have AD, and then you have BD and BE, and you have CD and DE. These are all the connections where you are finding. Those are nothing but the edges. And coming to the degree, when you are going to represent a graph, for that we need to represent the degree of it. What is the degree here? Here the total number of edges connected to a vertex is said to be the degree of the vertex. If you could see this example, for this, if I want to find the degree of A, how many edges that was connected to A, that will tell you about the degree. For this A, you have 2 connections or 2 edges that was present, so that the degree is 2. Okay, like that way we can find for each and every vertex. Now, what is in degree and what is out degree? What is the difference you are going to find with in degree and outer degree? Now, let us see. Here, in degree is nothing but the total number of incoming edges connected to a vertex. Incoming means like this way. Suppose I am having 2 vertices, the incoming means this one. The arrow which is pointing towards that particular vertex is nothing but an incoming edge, right? If I am having like this, then that is going to represent the in degree of the vertex. In a similar way, contrast to this, when you are going to see the out degree, the outgoing edges connected to the vertex is nothing but the out degree of that vertex. That means you could see like this, A, B, this is going out. From that particular vertex, it has to go out. That is nothing but an out degree. Now, when you are going to see about the graph, under the graph terminology itself, here we can represent graphs in different ways. One is using the directed graph and another one is using an undirected graph. This is a directed graph and this is an undirected graph. Undirected means you don't have any direction for it. If you can see, this is representing a single line. That means it is pointing from A to B as well as from B to A. Both the things can be done. And if you could see in directed graph, you have only one way. From A to B we can move, but we don't have any B to A. This connection is not there. Here only one direction we can move from one vertex to the other vertex. Now, if you could see how we can represent the degree over here, what is in degree and out degree we have seen, and what is the degree also we have seen. When you could see about the vertices of for each vertex, what is the degree, what is in degree and what is out degree here, or the degree is nothing but it is going to represent what are its in degree or out degree, both the things that will be represented as a degree here. So that here for an undirected graph, you will have the incoming edge as well as the outgoing edge. That's why always it will be 2. For every vertex it will be 2, and the in degree also the same and out degree also the same. And you could find the difference only in the directed graph. Okay, let us see here. These are the 4 vertices where you have. Now, let us check 1 or 2 examples so that you could understand what is in degree, what is out degree, and what is degree also, right? For a particular A vertex, the degree is, here you have 2 connections, right? Two edges are there, so that it is connected, it is represented the degree as 2. What is in degree? In degree is nothing but for this vertex, what is the incoming edge we have? That is nothing but the in degree. And if you could see the out degree for A, it is going only out, one edge is going out from A, so that its degree is 1. Now, check for this D. For D, the in degree is 0. You don't have any incoming edge, so that it is 0 and outgoing edge is 2. This is 1 and this is 1, 2. That's why we are going to represent with 2, right? And like this way, for directed and undirected graphs, the degrees are going to be different. And coming to the null graph, these are the different types of graphs where we have. What is a null graph? A null graph is nothing but a graph whose edge said to be empty. Whose edge set is said to be empty. That is nothing but you don't have any edges that will be present for the vertices, right? Actually, up to now we have seen this is a graph, right? These are the edges. These are the edges. But for this null graph, you don't find any edges. If you don't have any edges, that is nothing but a null graph. In other words, a null graph does not contain any edges in it. The same thing what we have discussed. This is the example where you can see the null graph. And non-directed graph or undirected graph, both are same. A graph in which all the edges are undirected is called a non-directed graph. You don't have any direction for it. And in other words, edges of an undirected graph do not contain any directions. The same thing that is repeated, but in other words we can say like this. And you could see you don't have any edges, any direction for these edges. This is nothing but a non-directed graph. And directed graph, if you see an undirected graph, it is completely opposite to it. A graph in which all the edges are directed is called a directed graph, and you are going to represent with arrow like this, right? In other words, all the edges of directed graph contains some direction, and this directed graphs is also called as, in short we name it as digraphs, okay? And here you can see these are the directions where it can move from one vertex to the other vertex. And the other one is cycle graphs. And what is this cycle? A simple graph of n vertices. If it is your n value is greater than or equal to 3, in that case n edges forming a cycle of length n is called a cycle graph. If my vertices are having 3 or more than 3, if I am going to consider, in that case how many cycle graphs we can form? Those are nothing but, you see, with the 3 vertices this is a cycle graph where I can form, and with the 4 vertices this is a cycle graph I can form, and with the 5 vertices just like a pentagon you can see, right? And for all these the vertices of degree is 2. If it is an undirected graph, you can remember that the degree of every vertex will be 2. And this is a cyclic graph, a graph containing at least one cycle in it. At least one cycle, that means it should have a loop, you should not go out of it. You should not have any break for it, right? That is nothing but a cyclic graph. You can see here, this is one cycle where it is forming, and this is a graph where it is forming another cycle. If you are going to have at least one cycle that is formed, then it is nothing but a cyclic graph. And acyclic graph, you could see the difference between the cyclic and acyclic. There we can form a cycle, but here it should not contain any cycles, it should not form any loops. That is nothing but an acyclic graph. And coming to the graph data structures, and here when you are going to represent your graphs, the graph data structure is going to be used in representing the graph in 2 ways. One is based on adjacency matrix and another one is adjacency list. In these 2 ways we can represent the graphs. Now let us see how we are going to represent the adjacency matrix. For this we need to follow some rules when you are going to represent an adjacency matrix representation. As we already know that how we are going to represent a matrix, right? Now in this representation, the graph is represented using the matrix of size based on the total number of vertices by a total number of vertices. That means in both the places we are going to represent the vertices, here in the row wise as well as in the column wise. In both the places we are going to represent based on the number of vertices. That means a graph with 4 vertices is represented. If I want to represent a graph with 4 vertices, how we are going to write? With size of 4 by 4, that means the matrix size will be 4 by 4. And in this matrix, both rows and columns represent the same vertices. Suppose I am going to have a graph with 4 vertices A, B, C, D. and ABCD. Like this way I am going to represent. This matrix is filled with either 1 or 0. In the matrix we need to represent only with 1 or 0 values. You should not have more than that. You should not represent 2, 3, 4 like that. You need to have only 0 and 1. That means 1 represents, what is the meaning of 1 and what is the meaning of 0? 1 represents there is an edge from row vertex to the column vertex. If 0 represents there is no edge from row vertex to the column vertex. That means if you have an edge, then we are going to represent it as 1. If you don't have any edge, then we are going to represent with 0, right? That is the meaning of it. Now let us see one example how we are going to represent the adjacency matrix here. Okay, for example, consider the following undirected graph and directed graph. Both the things, the same rules are going to be followed, and this is a graph where this is an undirected one. Let us see, this is a matrix where we are going to represent. Here we are having how many edges? Total 5 edges are there, that should be represented as in the row wise as well as in the column wise. And when you have an edge, we are going to represent with 1. Let us see one example. A to B, you have an edge, so that we are going to represent with 1. Suppose I am going to have A to A, I don't have any self loop, that's why we are going to represent with 0. In the same case, if I am going to have self loop D, in this case, observe D to D, yes, I am representing with 1. If I am having the self loop, then I am going to represent with 1. Otherwise, if you don't have any edge, represent with 0. And based on this diagram, you can check whether we have represented the matrix in the correct way or not. In the same way, you need to apply the same thing for the directed graph also. Based on the direction only, we need to write whether it is 1 or 0. If there is an existing edge, then we represent with 1. If it is not having an edge, then represent with 0. Okay. Now A to B, we have an edge, yes. And if you could see, A to C is also having edge. A to D, we don't have edge. A to D, we don't have edge, so that we are going to represent with 0. In the same way, we can fill the remaining values based on the adjacency matrix. Now, the next one where we are going to see about is adjacency list. In this representation, every vertex of a graph contains the list of its adjacent vertices. Just like how we are going to represent the linked list, here also we are going to make the links between one vertex to the other vertex if there is a connection, or if there exists an edge between those vertices. Okay. For example, consider the following directed graph represented implemented by using linked list. For A, what are all the edges we have? From A to B you have an edge, and for A to C also we have an edge. So that we are going to represent A to B and B to C. Like this, just like a linked list representation we have done. Right, all the vertices what you have, right? Now from B you have only one edge, so that B to D, and from D to E you have an edge, right? From B to D and D to E we have an edge, so that we are going to move. Next, from C to D you have only one edge, from there you don't have any further, right? So that we are moving to C to D. And from D, what are the edges you have? A is one, and D is one, and E is one, another one, right? These are the three another edges where we are going to represent D to A to D, and D to A. Any order we can represent, right? And the last one where we have is edge E. This you don't have any edges that was outgoing or outgoing from it, so that we are going to represent it as null. Null is nothing but you don't have any edges for it. And this is another way of representation. Instead of representing the links, we are representing in a single way of representation. Okay, and this is how the adjacency list will be. And the summary is, in this session we have discussed about the graph terminology like vertex and what are the edges we have, and we have seen about the different types of graphs, null graph, and we have seen about a cyclic graph, acyclic graph, directed graph, undirected graph, all these things. And coming to the graph representation, we come across adjacency list representation and adjacency matrix representations. Both of the things we have discussed. I hope you could understand this concept. Still, if you have any